I want to give you a little perspective of a little different talk than I sometimes normally do. I normally talk about Cray and all of our systems. I'll give you a little bit about Cray at the start here. But I want to talk just about the computing industry in general, and then specifically about high-performance computing and how I see that playing out. And hopefully we have some time to answer questions, and all of you can submit resumes because we're hiring a lot at Cray right now. So. All right, so at Cray, maybe just a quick perspective for those of you guys that aren't as familiar with us. We're all about supercomputing. That's really when we wake up in the morning, that's what we think about. When we go to bed at night, that's what we think about. And it all started from our founder, Seymour, who started the company in 1972, a snazzy dresser, as you can see there, and has continued on today. Really, the same kinds of reasons that he started Cray is the same kind of things that we're doing today, although the world of technology has changed a lot, and we'll talk about how we think it's going to change going forward. At Cray, we kind of do things a little differently. So we're a smaller company in the world of computing, but we spend a lot in R&D. Really, at our core, we're really an R&D company. We spend about over a third of our revenues in R&D, which is quite unusual for most companies. Today, in fact, I've never heard of another company that spends a higher percentage of their revenues in R&D in any industry. But we, as we develop our next generations of supercomputers, we develop it with a partnership in mind. And typically, this is one of our lines of systems that started with the Cray XT3, went to the XT4, XT5, then the XE6, which is part of what Blue Waters is, as well as the XK6, which is part of what the Blue Waters system is, and then our next generation machine called Cascade right now. But each of these systems, we started with a partnership with a customer or two, and develop them around the unique needs of that customer and the unique ideas of those customers, and then took that original concept and then expanded that into a broader market. And that's been a really fun way for us to build systems, because it allows us to be very close to some of the leading edge customers that we think are really pushing the technology forward, and have a vision for how that should play out, and then we integrate that with our own views and visions, and makes for some great discussion and debate, but also builds some great supercomputers overall. So that's been a very unique thing for us over the past little bit, and it's been very successful. So our company actually is the company, being a smaller company, we actually are the company that's built the most supercomputers at the petascale today. In fact, if you look at the 10 fastest supercomputers in the world, or even the 50 fastest supercomputers in the world, Cray has the most of those systems of any company out there. So it's a unique model and a unique design. But let's talk a little bit about how we see this going forward, and how we really believe that this landscape is changing a lot. It's changed a lot for us in the past. When we started in the 70s and 80s, we basically built 100% custom machines. Every single component in the machine was custom, and it worked immensely well. But then as the world of technology moves, you have to move with that. And today, a lot of our systems have a lot of commodity technologies and custom technologies in the areas where we think commodity doesn't do enough. And so it's a blend of trying to leverage as much as we can out of the world of commodity, but adding in kind of custom secret sauce in those areas that we think we can really make a difference and build differentiated products. And I think that's going to change again as we go forward out in time. So let's kind of break it down. This is my simple, I like simple things, and this is my simple view of the world of computing. So this is all kinds of computing. So in my world, there's 4 types of computing. So there's a traditional kind of enterprise transaction computing. This is doing things like payroll and ERP systems and things like that. That's one branch of computing that I think is obviously huge and has its own drivers behind it. The second one is big data, and this kind of moved from data warehousing and business intelligence and now is starting to really form its own branch of computing, and in fact at Cray we're very interested and focused in that branch as well. The third one is what I'll call scale-out data centers. So this is typically what you would find at an Amazon or a Google or a Facebook, where we're building out commodity technologies horizontally and scaling those out. And web search would be a good example of that. And then the last one is high-performance computing, and this is where we're typically doing science and engineering on systems. And all 4 of these have very, very different drivers, and in many ways they're going away from each other because of these drivers. So they're going up very different technologies, but some of those things are pulling them together. So we have this kind of tension in the overall world of computing of how much can you build a single system and leverage it across all 4 of these areas versus building 4 entirely unique systems to do each of these areas or some combination in between. And I think if we look at the business side of computing, and I've spent the last 9 years of my life at Cray, and before that I spent 13 years of my life at IBM. It's a tension that all companies are kind of going through, and it's a mix of technology and business. And those 2 things are really what's, I think, changing the world of computing, and is going to have a significant impact in the part that I want to talk about today, which is high-performance computing specifically. So in high-performance computing, there's a big problem, which I'll call it a problem right now, which is that the world of high-performance computing is bifurcating. And it's bifurcating into what I will call tightly integrated systems and loosely integrated systems. And loosely integrated systems, I think, are best represented by the cloud. So if you think about cloud computing, if you think about the kinds of systems that are being deployed there, I would say that that's how I see loosely coupled systems. And tightly integrated systems, I'm going to tell you, is more like Cray, what Cray does, which is build those technologies that allow you to much more tightly integrate these systems together. And so the world of HPC, in my mind, is bifurcating between a cloud or a Cray. And I think what's going to get caught in the middle, quite honestly, is technologies that are in between those. So I think a lot of what we think about today with commodity clusters with a little bit better interconnects like an InfiniBand, I personally believe are going to get caught in the middle of this bifurcation and fundamentally actually not be successful longer term as we go forward, because I think it's either going to move. You're going to either want to do something more economic, which is like a cloud, whether that's a public cloud or a private one or whatever, or something much more tightly integrated to get the kind of performance and capabilities that you need, which would be more like a Cray. Now, there's a lot of different things that you could start talking about. One thing you could talk about is, will all of HPC move to the cloud? And there was a really great study in the Department of Energy that was done looking at EC2, which is Amazon's cloud, and I've given you guys the link here if you want that. But it said that it's 6 times slower than a typical mid-range Linux cluster and 20 times slower than a modern HPC system. And by the way, that modern HPC system was a 2-generation-old Cray machine compared to the cloud environment that it was being compared against, oh, my thing is trying to synchronize. I think that that's a good example that I don't believe that all computing is going to go to the cloud route. And I clearly don't believe all computing, although I dreamt it a couple times, all computing will go to a Cray. But I do think that this bifurcation is causing a lot of what is going on in the world of technology, even at the component level of technology when we think about processors, memory, networks, and software. So you could ask the question, what about a Cray in a cloud? You can definitely do something like that. So could we do a tightly integrated system within a kind of a cloud environment? You definitely can do that. In fact, that's a lot what supercomputer centers are, really, is putting a big supercomputer in a cloud. But I'm not talking about that. I'm talking about the underlying technology that's being used, not the way you access that technology, which is really about a Cray in a cloud. And one thing we asked ourselves at Cray is could you use supercomputing, tightly integrated supercomputing technology in a cloud environment and get value out of that? And we actually did a research project with Microsoft Research, which was doing their cloud computing research at the time, and said, could you apply power packaging and cooling technology, so kind of energy efficient packaging technologies that we've developed in our supercomputers, and can you apply that to a cloud environment and drive down total cost of ownership? Because cloud computing at its core is not a computing model, it's actually an economic model. It's all about economics. And so it's all about driving total cost of ownership down. And so we had a set of goals that we jointly agreed on, which was a 75% TCO reduction, not having to require using chilled air or water, because we wanted to be able to put these in anywhere around the world. You can't have raised floors anywhere in the world. We want to, put them in containers and things like that. Be able to use 100% free air cooling year-round in many environments. Over 1,000 processor sockets in a single cabinet, assuming about a 40-watt processor, which is typically a processor that people are using in cloud environments today. And a number of other requirements. In fact, even going up to 122 degrees Fahrenheit. So could you have a machine that literally can operate in that kind of environment, and a PUE, for those of you that are familiar with that, of near 1 year-round. And we actually had a goal to do this within 2 design cycles. So do kind of a first prototype, and an engineering artifact, as Microsoft like to use, and then secondly build a system that achieved this. And we basically got there with the first prototype. And this is literally a picture of what that looked like. You can see we had to deal with a lot of different things. We actually had to, the cabinet's not rectangular. You can see it starts to get fluted there at the top because of the wind, basically the airflow. It just allows you to be much more efficient. The blades are all not lined up like typical blades. They're off center on each blade to allow more efficient airflow and all of this. So there's, I think, a lot of great work that can go on to utilize technologies from tightly integrated systems into loosely integrated systems and vice versa. And you're seeing that today, and this is just one example of something that we did that is some pretty cool technology that was developed. Lots of this will start to come into play in our future systems as we go forward. So if I think about then what does supercomputing or high-performance computing look like in the future, it's really going to be almost solely focused on scalability. Because even at an individual workstation level, where you're going to get many more cores on a single workstation, to the largest supercomputers in the world, it's going to become more and more about how do we take advantage of scale. And how do we use that so that when we add more processors in, we don't get fewer performance increments out of the machine. And also the other big thing that's going on is that in an individual processor, what we're doing is getting more and more lower powered cores. And so these cores are not getting faster like they have been for the last 10 years, but they're actually getting slower over time, each individual core. And you're getting a lot more of them. So when you start to get into that, you start to think about, is there other kinds of novel architectures that you can use that maybe you could take better advantage of? And these two big trends, I think, are driving a lot of the thinking right now in high-performance computing and how high-performance computing is going to evolve over the next few years. Scalability is something that is really happened, and it's really started around 2005. 2005, anybody know why this scalability trend changed? So all of a sudden the curve shot up. Anybody got a guess on that? A yell? Yeah? Pardon? Multi-core. So 2004, 2005 is when AMD and Intel both kind of started coming out with multi-core. And all of a sudden now, this is a chart of the top 20 supercomputers in the world. You can see that this trend continues. In fact, in 2006, if you looked at the 500 fastest published supercomputers in the world, there was about 1 million cores in all of those systems. This year at this university, you'll have a system which you could technically call about 2 million cores, if you count each of the GPU cores and each of the CPU cores in a single machine. And by the end of the decade, in a single machine, we'll have 1 billion cores. And so this trend is going to continue in a huge way. And dealing with this scalability issue is a big part of what's happening in the world of high-performance computing and how this is going to play out in time. And when we think about kind of the future architectures of supercomputers or high-performance computers, there's really two general designs. One is a homogeneous design where all the cores and all the processors are the same in the system, and another design, heterogeneous design, where you have different types of cores and processors in the same system. And we could have picked many different computers to show you an example of. Since I got to do the chart, I got to pick what computers, and of course I picked Cray computers. So this is on the homogeneous architecture. The good example is a Cray XE6, where we have the standard AMD Opteron processors, and in the hybrid architecture we have an XK6, which has a combination of an AMD processor and an NVIDIA GPU. But what's happening is at each of these nodes, which, by the way, is a very similar node that you can have on a workstation or a cluster or a supercomputer. The nodes are virtually the same building blocks. These nodes are getting much, much more powerful. And so we're starting, more and more the bigger issues are around system balance. So how do you balance out this very fast-growing performance at the node? How do you keep it fed with data so that you have high efficiency? Well, in the world of transaction processing, remember the first category of computing, the way that you do that is you use software that basically takes a node and creates a bunch of virtual machines and makes a single node look like a lot more nodes, and you basically simulate a lot of nodes on a single node. And that's how you try to get more utilization out of each node. When you're doing high-performance computing, we want to use these nodes all together, and so instead of breaking them up, we want them to work more together, and we want to keep data filled into those nodes. So what we do is balance that off with higher performance interconnects and software that allows us to move data around the machine much, much faster. But this tight integration is what becomes more and more important as these nodes grow in size, which is why we're getting this bifurcation of the marketplace overall. So one of the big things that's going on is around hybrid computing, or these heterogeneous architectures. And our view on accelerated computing or hybrid systems or heterogeneous systems, however you want to call them, is that this is a trend this is not a fad or a trend. This is here to stay. These kind of technologies are very important and here to stay. An example of a trend would be this, right? So people that wear their pants below their butt. This is a trend I hope ends pretty soon, by the way. I hope my daughter's friends stop this, but this is a trend. Heterogeneous computing is not a trend. And there's a lot of reasons for that. One of them is that Power, so power utilization. So what's becoming more important now is that we can't continue to increase the power wattage of each of these processors. So we have to do things to kind of control that, cap that, and the way to do that is not do scaling of frequency, which takes tons of power, but just add in a lot more lower frequency processors. So we're having this to deal with this kind of an angle. There's this huge trade-off, though, of getting easy performance versus being much harder to program. And so this trade-off is something that's being worked on a lot, including at companies like Cray, who are investing a lot in trying to figure out how to make this trade-off much less abrupt than it is today. Today, if you want to use, for instance, a GPU for computing, it takes a lot of work and a lot of energy to do that. We need to lower those barriers so it's much more productive and you still get a lot of the performance. So you can use them much wider across a much larger range of different applications. But what's really interesting, I think, as we look out into the future, is that these accelerators, as they look, and what current just standard Intel and AMD processors look today, gets very blurry. Because we start to see these, today, for instance, on a node, you'll have a hybrid node. You'd have an AMD or Intel processor and an NVIDIA GPU. In the future, all of that will be fused together on a single piece of silicon. And so it becomes very blurry of what you call an accelerator or a many-core or a GPU and a CPU. And because of that, we have to start thinking about programming these things that are portable, programming languages and such that are portable, not just across technologies, so you can have a single source code across a CPU and a GPU and Intel many-core accelerator, but also over time, because these technologies are changing over time. And we don't want to, every time we run our application on a new machine, we don't want to have to reprogram that or have a different source tree for that. So that's a big driver right now overall, a huge area that we at Cray are investing in, from the programming environment, compilers, libraries, tools, etc., to kind of hide this complexity from the users. I think a great example of this is something called OpenACC. So this is an open programming standard for parallel computing. It just got announced in November of 2011, which allows you to have portability across a large number of systems, processor technology, compilers, CPUs, accelerators, everything, all from a single code base across Fortran, C, and C++. And it's a partnership with not only Cray, but a company called CAPS in France, NVIDIA and the Portland Group, and hopefully many more companies over time adopt this standard as really something to build to, so that when we take our applications, we can do them once in this kind of environment and move them forward and across different technologies. Just a quick example. So we actually took a kernel, not a reasonable sized kernel, so about 6,000 lines, and we decided to do a node-to-node comparison. So many times when you see accelerators compared to systems, you'll see people compare a GPU and a single CPU, or a GPU and a core of a single CPU, which is always something I don't encourage. So what we looked at is a total hybrid node, a CPU plus a GPU, versus two CPUs. And looked at the speed up that we could get from that. And so we did this work with the NVIDIA CUDA compiler, and we basically had to end up rewriting the whole application. So we rewrote the application. It didn't look very similar to the existing kernel, and we got about 1.3 times speed up node to node. By the way, if you looked at that from just a GPU to a CPU, that would be a speed up of about 3.5 or something. We did the same in OpenACC. We only had to change 20 lines of the code, and we actually got better speed up. Now, sometimes you won't get better speed up, sometimes you will. That's actually not the important thing. The important thing is the lines of code that we had to change. And so this is just an example of technologies that are starting to come out to lower the barrier to adopting these kind of new types of computing paradigms that are out there to drive much much better price performance over time and much better efficiency of your overall system. But when we think about computing in high-performance computing or petascale or even exascale computing, we have to think about it as the whole environment and not just the system, not just the processors. And so we talk about petascale computing versus petaflops computing, or exascale computing versus exaflops computing. And a lot of it is around the amount of data that's being generated and this whole world of big data that's starting to impact us a lot more in computing than has in the past. And as we grow, as we build bigger and bigger supercomputers, we have faster and faster simulations, we generate more and more data, and we have to then deal with this data, of course. And so one of the things that we're very focused on is trying to do this type of enablement across this whole environment. And so you have your computation or simulation environment, together with a data storage environment, together with a data analytics environment, and bringing these environments, enabling these environments for folks. And so when we think about the computation environment, what we're most focused on at Cray is helping with programmability, just like this open ACC. So how do we build better tools to allow you to better use these systems? And this is what a lot of people are doing in the industry. In the storage environment, it's all about enablement. How do we enable people to use both the analytics and a computation environment? How do we make that not a bottleneck for people, especially as data requirements grow more and more? And when we look at analytics, we try and help people around finding different relationships in their data. So how are two different people connected to each other through what way of a graph? Think about a Facebook graph, for instance. How do you really find hidden meaning within all of that data that's out there? And at Cray, we do this through something that we call adaptive supercomputing, which is basically about bridging all of these environments together onto a single platform over time. Many other companies are doing it in other ways, but this is really how HPC is starting to evolve. I think a great example is a system that's here at NCSA, Blue Waters, a very well-balanced machine that looks at the computation simulation side as well as the data side. Much, much better, I think, than most other supercomputers out there today. But you can kind of see from this perspective that you can kind of start to put these environments together in a less tightly coupled way than we want to move as we go out into the future. So our vision as we move forward from the world of petascale computing like we are today to the world of exascale computing like we'll be at the end of the decade is to really build a computing environment that bridges science, engineering, and advanced analytics applications. And we want to do that by building this common scalable framework that we can then put in different types of processors into the same framework to do different types of applications. Layer on top of that an open source operating system like Linux optimized for the environment, and then build what we call an adaptive software layer on top of that, which allows you to start to build these programming tools, compilers, libraries, all this environment to kind of shield the user from all the underlying complexity of these machines as much as we can. And there's a lot of challenges, though, as we think about the future. So in addition to the programmability side and finding relationships in our big data, there's a lot of issues that are just core to getting to the next generation of computing. And so exascale computing is generally thought to be at the end of this decade, whether it's 2017 or 2018 or 2021, who knows. But roughly in that time window, there's generally considered four major issues that we all have to deal with. One is the power usage. If you scaled up today's computers up into that time frame, we would not have computers that are 10 or 20 megawatts. We would have computers that are 100 to 1,000 megawatts, and that drives a significant cost of ownership that's probably not tenable for most people. The second is concurrency. So we have all of these cores. Remember that on a typical processor of this time, whether it be an accelerated processor or a standard CPU, you're going to have between 100 and 1,000 cores. And that includes, by the way, on your laptops. And so how to use that environment is going to be very interesting. There's a lot of work being thought around that. But how do we, every time we basically do a calculation, keep all of these cores in use? And how do we program this kind of machine? And how do we deal with the failures that's going to happen when you have billions of components in a machine? And by the way, this resiliency, a reliability issue is as much in the storage subsystem as it is in the computer, because the storage reliability is actually getting worse faster in comparison to the computational side. So I just would like to give you an example of what a system like Blue Waters might look like at the end of the decade. So this will be basically a concept of what an exascale system looks like. I think it looks like a big headache. And so 250 cabinets, so very similar in size at that time. Each processor will be in the range of 10 to 15 teraflops. Each cabinet would be 5 petaflops. So that means in about 3 cabinets, that's about Blue Waters. So it gives you a perspective of how dense these are going to be. About 1 billion threads, over 100,000 sockets on the machine, and you'll have different levels of memory. So you have some memory on socket, which is small but very fast, and some memory like we have today with DIMMs off socket, which is slower but bigger, and in the range of 20 to 30 megawatts. And I think Blue Waters is around 12-ish is projected. 12 or 13. So kind of a factor of 2 or 3 over that today. And this is kind of as we see the technology today and how we see it evolving with some of the research that's going on at places like Cray, but many other companies like IBM, NVIDIA, Intel, AMD, etc. Today. Okay, so when we think about this kind of evolution of HPC, we think about processors having hundreds to 1,000 cores, from all the way from the desktop, so scientists and engineers doing work on your desktop, versus going all the way up to the largest systems in the world, basically using very similar types of cores because of volume and kind of the economics of HPC. But at the same time, we have computing models that are bifurcating from loosely coupled systems, as I mentioned, cloud, to very tightly integrated systems like you have on Cray. And therefore, a very tightly integrated, holistic approach is really required as we design high-performance computers in the future, really focusing around scalability, around balance, and around programmability. And so when I started today, I showed you a slide of our founder, Seymour Cray. I'll kind of end with a picture of Seymour. And this is one of my favorite quotes that Seymour had not so long before he passed away, which is, "The future is seldom the same as the past." And I think this is a great quote. And it's from a guy that kind of invented the world of supercomputing and saw how that changed over time between the 70s, 80s, and 90s. And I think that we see the same as we think about the 2000s and out to the next couple decades, which is that we can't rely on the kinds of systems that we've had in the past, because the business side of technology, the economics of it, are not going to allow that to play out into the future. And so we have to get this shifting of where technology moves, how to take advantage of that, and where do we put our emphasis and focus. So not in getting a faster single processor, but how do we start leveraging these many core processors that are out there in the marketplace and will continue to be out there over the next 10 years. So with that, I just want to thank you and maybe open it up for some questions if we can. So the fun part of this is somebody has to start with a question. Yes, please.
First, I'd like to thank you for the wonderful lecture and also for the machine. Workers actually started yesterday. It was absolutely outstanding.
Oh, that's great.
And it's just as good as a machine that is well tuned over the years.
Thank you very much.
But now I have a very tough question to you. I'm in the field of life science, computational life science. have there David Shaw, and he has a machine built that's 100 times faster than everything else we have.
Yeah.
So with your machine, you can do more.
Yep.
What? There's some lesson you can learn from their strategy to make, nevertheless, you said it's possible to do nevertheless a little faster, because that's what we are hunting for.
Yes, I think that's a great question about specialized architectures. In fact, 2 years ago, we built the fastest FPGA computer in the world. We just did it for the intelligence community, so we can't talk about it too much. But I think definitely in computing, it's not a one-size-fits-all environment. Just like I don't believe that you can do real, true, tightly integrated supercomputing well on the Amazon, EC2 cluster, cloud environment. You can definitely go and build what I'll call special purpose machines that do one algorithm or one calculation or a small set of calculations better than anything else you can do on a general purpose machine. So I think you start to get into this trade-off space of if you really have a single kind of way that you want to solve your problem, and you know that as you scale up your problem and move forward that you're not going to change that, because actually that typically does change as you move from one scale to the next scale, then you can build very I think unique specialty kinds of machines like the Shaw machine. I forget what it's called. Yes. Yeah, Anton. And so you could build machines like that definitely, do those things very, very well. Better than any general purpose system will do. The problem is you can only do a few things on those machines. And so I don't think that it's very scalable from that perspective. What we're trying to do more and more, and by the way, our system in the world of big data is very similar. So we do graph analytics. So if you have a graph algorithm that you're doing on the machine, and we actually are using kind of linked or semantic data on the machine. If you're doing semantic data or linked data, you can do it about 100 to 1,000 times faster than you can do it on a traditional machine, because we have a very unique architecture. What we're finding, though, is that in the world, as technology is progressing, we're starting to be able to simulate a lot more of these, what we do in special purpose machines, in general purpose machines, much more cost effectively. So I do think that I think special purpose machines will have a good advantage when they first come out over traditional machines, but will quickly get eclipsed over time as technology shifts and with the changes in technology. So I think an FPGA, which is very hard to program, for instance, if you look at a GPU or a common accelerator, much easier to program, not as easy as a standard processor, but much easier. Those technologies will converge and eclipse over time. And so I do think that more and more of those kinds of things will be done on systems by leveraging some of the custom technology and some of the commodity technology. But I always think at any individual point in time, you'll be able to build a better special purpose machine for a single problem. I think that will happen, by the way, forever. And I think that's natural, right? So, if you want to drive a fast car, you can get a Ferrari. In fact, I was just at the University of Stuttgart dedicating their machine not too long ago, and Porsche does all of their computing at the University of Stuttgart. And I had the opportunity the 2 weekends before to see the new Porsche 911, which, if you've seen it, is a pretty awesome car. And I was kind of jabbing my wife and said, hey, we should get one of those. And she said, yeah, our 3 kids would fit great in the back seat of that car, right? And there is no back seat of that car. But So it doesn't do everything that you need, right? And so I think with general purpose machines, I think more and more we get the benefits of having something that can take a wide variety of science and engineering kinds of applications for high performance computing and start to do some of these specialty things either in software or by leveraging some of the custom hardware that's coming out into the future. So I think we're going to get closer and kind of reduce that gap, but we'll never completely reduce it because you know, that's just what a special purpose machine is all about.
But you said that the processors become even slower.
Yes, but you get so many more of them. And so if you can take advantage of the scalability, you can take advantage of that. For applications that can't scale, then we have to look at algorithmically how we deal with that. Yeah.
The past couple of decades, we've seen the rise of massively parallel supercomputing applications,
Mm-hmm.
What do you think are the things that are maybe a little bit obscure in these application areas now that in 5 years will be front and center in the supercomputing world?
That's a great question. So I think that there's a lot of disciplines that aren't even touching computing. I mean, biology is barely getting there today, right? So it was probably late 90s that we all really got in high performance computing really excited about life sciences and how that was going to be the next big application, kind of killer app for high performance computing, and that came along really slowly because you know, you're not just dealing with the computational problems and the algorithmic problems, you're dealing with people that were used to doing something in wet labs now wanting to do things computationally. It's very hard. I personally think arts and humanities is a really great area that we're starting to see a lot more interest in that we haven't really seen done computationally. We have one guy that's approached us around music and doing doing that computationally, which is very interesting kinds of approaches. So I think that those areas are really interesting. I also think we were talking earlier in one of my other discussions today, agriculture. I think that whole area is a big area now. I've spent some time with companies like Monsanto and such around this. So I'm starting to see it in a lot more areas such as that, so that are going to adopt over time. Yeah.
Hybrid computing more of that is not a new problem. So what do you think has changed that means that hybrid is optimized well for architects that think that different length there it's a classically different problem.
Yeah, it is, and there's always this view that compiler magic will solve all problems, right? And it never does. And so I'm careful about that. But I would say that what we found. We actually stopped doing compilers at Cray. So we used to have our own vector processors, and we did our own compilers for our vector processor line. And for our x86 kind of line, so our MPP systems, we just basically used commodity compilers from Intel or Portland Group or whoever. And what we found is as things started moving to multi-core, the way that in vector computing you start to set up your data on the machine to get the best utilization out of it is very similar to the world of multi-core. And so there's difference in vector lengths, and there's other issues that will have to be dealt with. But and it convinced us that we should actually take our vector compiler and technology and move it to the world of x86. And we've just done that. It's very new, so we have a very new compiler in this area. We're kind of just focused in specific areas. It's not a broad general purpose compiler yet, and we're debating about how broad and general purpose we need to make that over time, but we've had tremendous success on it. And the other exciting thing is that companies such as NVIDIA that were working on CUDA or AMD that were working on things like OpenCL have also realized that those are great, amazing languages to help to make GPU computing easier. but they're too hard to get a broad set of people to use that. And so I think what you're starting to see in the world of compilers, and especially in compilers, is that people with lower expectations of pure performance trading off programmability and ease of use. And I think for one of the first times within high-performance computing, we're actually seeing that trade-off being made all the way, not just in lower-end systems, but all the way to the largest systems. Because time and programmability and being able to move your application across all different architectures, because nobody wants to build their application for just one machine, unless you're using Anton. You know, that is becoming more important than whatever the pure performance that you get out of any individual machine. So I think that there is a lot to be said there, but I don't think it's you know, magic pixie dust. So there's still a lot of work to go on, and I think that what we need is a programming environment that incorporates compilers, but more tools and libraries that help us to do that. Yeah.
So it goes back a little bit to Klaus's point, but slightly different. If you look at your numbers for the amount of flops and number of bytes available on the machine, that ratio has
Bytes of memory?
bytes of memory,
Mm-hmm.
bytes of DRAM.
Mm-hmm.
It's the DRAM is getting lower and lower compared with the number of flops.
Just wait, it's going to go
It's
worse.
going to get much worse. We projected to 50 petabytes
Yeah.
for a machine.
Yeah.
There are application reasons, applications that are possible for that. We don't want to go to larger and larger. We do want to go to larger molecules, but there are biologically relevant molecules that are that we can work on.
Yeah.
So all of these points to as we go further.
Yeah.
And strong scaling requires the very tight 90 critical path would be maybe a millisecond. I mean, so we would like to do a time step in a millisecond in many applications. Whatever the number of processes that approaches that to process in a millisecond. To break that, seems tough. And it's a technology dependent. What can you say about the strong scaling?
So I would say that there's a number of technologies that are being thought about in the world of trying to get more memory and faster memory onto a node. I think that in general for supercomputing, it's not going to be so cost effective. But I think what you're going to find is a subset of nodes within a supercomputer, or in just a high performance computing system, and maybe a system that is built more tuned to those kinds of applications versus the broader other set of applications. I think it's going to be pretty expensive to do it any other way, because the technologies that you have to develop, so like 3D stacking and different technologies that are kind of going on right now, are very, very expensive. So it could give you the capacity and the bandwidth that you need to help you with kind of strong scaling things, but will not be as cost effective, because they're not going to be general, you know, they're not going to get the kind of commercial pickup. Yeah.
I think the bottlenecks are more in the nature of hiccup-free, fast, low latency communication across nodes.
Well, that I think is going to get better, because I think more and more of the technology to interconnect nodes is going onto the silicon and onto the processor silicon, which is a faster silicon than typically the interconnect silicons are today. So I think that will actually do a lot better than it has been, because to date, the interconnect technology gap between the silicon IC generation and the interconnect IC generation has been increasing, which means processors getting faster, much faster than the interconnects. I think that you're going to start to see subsets or even all of those interconnects back onto the same generation that the processors are on. So I think we'll get some relief in that side. I think the memory side is still very tough. Yeah. Was there a question back there? Yeah.
You mentioned that you see the like the GPU processor.
Yeah. So we are going to clearly get more levels in the memory hierarchy than we have today. So all the way from all the caches, there's consideration of even closer caches than we have today than L1. So between registers and L1, and then a lot between where L2 caches are and main memory, and then a level or two past main memory. So there's the memory hierarchies, there's a balance there. So when our hardware architects they talk about, they could show you something with like 7 levels of basically memory hierarchy. And our applications guys would say, please do not build that machine, Pete, because we will never understand how to use that machine. It's just too complex and too complicated because some of the caches are coherent and some of them aren't. And so I think that the big challenge for us as manufacturers is going to be, where is that balance between usability and what's possible? And that, I think, is a big debate right now that's going on within the computer architects today. Not me, but our architects at Cray, as well as within the industry, by the way. Yeah, John.
Let's test the crystal ball a little harder. What I've noticed over the last 20 years is there have been occasional, and you made this point about Anton being sort of specialized architecture that has an advantage for a brief period of time, but it gets overtaken by the commodity processor, in that case, the commodity technology. There have been a few instances in which that specialized technology actually became incorporated into the mainline technology, usually driven by some other commodity drive. So I think 2 key examples are when you went from custom processors to commodity processors. And what we're experiencing now as GPUs are becoming commoditized in the HPC space because they were driven out of a different place, as were the commodity processors. So those give us a run for a while. And then there has to be something else. Any idea what's next? As advantageous technology, it doesn't simply get overtaken by the incremental engineering improvements of the existing technology, but actually get adopted into the
Yeah, I think it'd be too easy to answer that to say something like, ARM, mobile processor technology or something like that, because I think that is also blurry and is going to be, I think that's a natural, so I think that that's a too easy answer to that question. I think what we're gonna see more of is, as we were just talking about this a little bit ago in another discussion I was in. So a piece of processor silicon that you want to sell to a market, like let's say at $500 or $300, but pick your price, that then you got to create for half that cost. When we start moving further and further with IC technology, and I was just with one of the CTOs at Intel who said, we see Moore's Law, we can extend that out through exascale at least, and probably beyond a little bit there. What we find is, as you start to shrink these things, more and more we get free silicon to use. And what we're seeing more and more is not necessarily, I don't believe, different kinds of processor technology making its way onto that silicon. I see the next level of integration technology making its way onto the silicon. So I see kind of parts of interconnects, networks being put onto the silicon, or special functions that we can leverage being put onto the silicon, but that's because of the silicon shrink. I can't point to outside of something like ARM processors, or let's just say mobile processors in general. I can't point to a specific technology that I would say that I think right now we see as a very viable candidate of moving into that. Clearly mobile, but beyond that, I can't see that. So my crystal ball isn't so good there. Yeah.
Process that because of the way that, present connections are all.
Yes.
So I heard that Intel and amount of energy.
Yes.
So how do you think optics is going to be a factor in future?
Yeah, I think it's going to be huge. And I think it's not just going to be huge on the silicon. I think the next connection off the silicon will start to move to optics for the same reason. But you're right in that it's not it's not generally considered the best technology out there for power, but it seems like the one that's most manufacturable today. In large quantity, and so that's why it's kind of the leading candidate right now. Beyond that, there's other technologies that people are starting to look at, but clearly I think it's going to be a very big deal. I think that there's also manufacturing process technologies of stacking not only memory but processors, putting processors in the memory, PIM technologies that we've talked about for many years, which I think are actually starting to become much more viable now. That will start to help that. But definitely moving data costs way more than computing data. And it starts to, I think it's also going to change that it's going to be cheaper to recompute instead of store data out into the future for a lot of what we do. We're not going to be able to do that for everything, but I think many times that we're going to make that trade-off too. Yeah. Yeah. Hi.
So I'm from the storage side of things. We talked about live. Where do you see storage next?
Yeah, I mean, I think the things that we believe that the current kind of HDD technology is going to continue to prevail even in exascale. So we don't believe as of today, and this is, I'm speaking for our storage guys, that while there be utilization of things like SSDs and kind of future solid state technology and stuff, it will be in very select areas. Even in our current device that we have now, Synexion, we have SSDs, doing some of the work in that, but very small as a percentage of the overall storage, and that's really driven by economics. The bigger concern that our guys have is reliability in the storage devices. And because you have a lot more of them, it's much harder to do application level resiliency in a storage subsystem than it is on a computing system. And so I think that that's going to become more and more of a challenge, and so technologies to kind of work their way through that. And then the other thing is we see PNFS becoming a much more viable out over the next few years, and being much more pervasive as a way that we can do that, although we still believe that there'll be optimized clients to get faster performance. And so so those are kind of the general trends. I would say that trends in the storage space are less clear than they are today in the processor space because of the technology shift. Yeah.
One more question, and then I think we'll have to wrap up.
Thank God it's higher level, by the way. I cannot point to a single unfortunately, cannot point to a single commodity driver towards single thread performance. And that's a huge issue, I think, for us. Because in a real heterogeneous system, what you'd love to have is a lot of really fast, 1,000 fast parallel cores, low power, and a small number of really, really fast single-threaded cores. But we don't see much driving that right now, and unfortunately, I think that's why we're seeing more and more, even at the technology like Microsoft with Windows, right, doing a lot more around. They have huge efforts in the company around taking advantage of these things because it's an inevitability, and we're going to have to deal with it, and that's all the way to the desktop. and all the way even in cell phone technology. So think about it like a 150 gigaflop cell phone or something. You know what I mean? It's incredible what kind of technology that we're going to have. So we really are going to have to adopt this and try to make it work. And that's why I spent some time around this programmability piece of things, because that's going to become just absolutely critical. I actually think it's tougher at the desktop level than it is at the supercomputing level. When you're dealing with a few of them, it's harder than dealing with, you know, kind of saying this is everything, right? Because you don't get as much benefit potentially out of that, so the payoff isn't as much.
The University of Illinois' National Center for Supercomputing Applications provides powerful computers and expert support that help thousands of scientists and engineers across the country better understand our world. With the computing power available at NCSA, researchers create computer simulations with real-world social and business impact. NCSA is supported by the State of Illinois, the University of Illinois, the National Science Foundation, and other federal agencies.